Here is one additional thing that we need to know about equilibrium. This is probably the most challenging part of accelerated chemistry. It's generally taught in AP. It's kind of a surprise to me this year that I would be teaching this as an accelerated component, but it does give a good preview for those going on to AP or for those who are planning to take the chemistry SAT too. And since I'm teaching it, it will be tested, and the key is just to think your way through these problems. We'll begin with this problem. When 1 mole of ammonia gas and 0.4 moles of nitrogen gas are placed in a 5-liter container allowed to reach an equilibrium at a certain temperature. Remember, each of these equilibrium constants and equilibrium concentrations applies to specific temperatures and specific pressures. It is found that 0.75 moles is present. What is the concentration of each species? So the first thing we need to do in an ice table, if we want to call it a rice table, we have a reaction in addition to a initial concentration, a changing concentration, equilibrium concentration. But in this case, because I start with ammonia, 1 mole of ammonia, yes, I do have some nitrogen in there, but I don't have any hydrogen. So hydrogen has to be a product, which means nitrogen needs to be a product, and ammonia is my reactant. So that's the beginning portion of this calculation. And then if I'm thinking about equilibrium constants here, it's products over reactants. So I need to set up my equilibrium constant expression with products on the top and reactant on the bottom. There only happens to be one reactant. Each of these concentrations, remember the brackets mean concentration, each of these concentrations are raised to the power of their coefficients. So hydrogen gets raised to the power of 3 and ammonia gets raised to the power of 2. Next trick is to find equilibrium concentrations. Now, I wasn't able to animate this table as I had hoped, but we have 1 mole in 5 liters. So 1 mole per 5 liters. You divide it to moles per liter, that's 0.2 moles per liter. And then 0.40 moles in 5 liters would be 0.08 moles. As I said, we start out with 0 hydrogen, so we have 0 moles of hydrogen. Now, the changes for every 2 moles of ammonia that decompose, 1 mole of nitrogen and 3 moles of hydrogen are produced. This comes directly from my original equation. 2 moles of ammonia, when 2 moles of ammonia decompose, I make 1 mole of nitrogen and 3 moles of hydrogen. Now, I was given the answer that 0.75 moles of ammonia remain at the end when the system has reached equilibrium. 0.75 in 5 liters means 0.15 in 1 liter. Excuse me, a little bit of a yawn there. And the decline in my ammonia was matched by an increase in hydrogen. Now, I'm using an old version of this because my computer crashed. So let me fix that. And here we are. So my ammonia concentration declined. For every 2 moles that would decline, I would get 1 mole of nitrogen, designated as X. I did start out with some nitrogen. So my nitrogen that I started out with has to get added into my X, which is the amount that is increased when molecules of ammonia decompose. And then for hydrogen, I have, for every 2 moles of ammonia that decompose, I get 3 moles of hydrogen. I start out with 0. Whatever the amount is that ammonia decomposes, I'm going to get basically a half of the amount of nitrogen and then 3/2 of the hydrogen, if that makes any more clear. So what the overall situation is, concentration of ammonia changes from 0.2 molar to 0.15 molar, which means for every liter of ammonia gas, 0.5 moles or 0.5 moles per liter decomposed, which would mean that my nitrogen concentration would increase by half of that value because it's a 2-to-1 ratio. So it'd be 0.25 molar, which is designated as the change in X, and hydrogen would have to be 3 times greater than nitrogen because the ratio is 1 to 3, which means I have a 0.075, which is 0.025 times 3, which is 0.075 molar. Now I need to plug those concentrations into my Kc. Now, Kc is exactly the same thing as Keq, exactly the same equation. C only refers to concentration. Those letters designate different forms of calculating an equilibrium constant. Don't let that confuse you. This is the K, the equilibrium constant for a particular concentration. You do not need to worry about defining Kc in any other terms. It's the same exact thing as Keq. Now I plug in my values. Sorry, another yawn there. 0.105 molar. That comes from my nitrogen because it was 0.08 times 0.025 is 0.105 molar. I raise my concentration of hydrogen to the power of 3, and I raise my concentration of ammonia to the power of 2 in order to calculate my equilibrium constant, which gives me an equilibrium constant of 0.00197, which in this particular case, remember, I started with ammonia, that's my reactant. These are my products. In this particular case, the reactants are favored because the number is less than 1. And look at my concentrations. My concentration of ammonia is higher than my concentration of nitrogen and my concentration of hydrogen. So this all should pretty much make sense. The next one is a bit more complicated. Here we have a calculation where we don't know the original equilibrium concentration. 4 moles of hydrogen iodide are placed in an evacuated 5-liter flask and heated to 800 K. The system is allowed to reach equilibrium. What will the equilibrium concentration of each species? What will be the equilibrium concentration of each species? Actually, that does make sense. I don't need to fix that. If the equilibrium constant at this temperature is 0.016 K. Now think, just for an example right now, if I raise temperature, I'm going to jostle around my hydrogen iodides a lot more, and I'm going to end up making the only 2 things I can possibly make from hydrogen iodide. I can make hydrogen and I can make iodine. No other possibility. Now, as I did say in class, hydrogen iodide is a colorless gas. If I start to watch this system move towards an equilibrium, I would actually start to see a purple vapor coming from the iodine gas. Iodine is a solid at room temperature, however, it sublimes very, very easily into a purple vapor. And just from my Kc already, I can tell that my concentration of reactants should be higher than my concentration of product because this number is less than 1. Now, to take a little bit closer look at this, 4 moles in 5 liters. That means my initial concentration of hydrogen iodide is 0.800 moles per liter, 0.8 moles per liter. 4 divided by 5 is 0.8 moles per liter. I start with 0 hydrogen, I start with 0 iodine. Now looking at my equation here, for every 2 molecules of hydrogen iodide that decompose, I make 1 molecule of hydrogen and 1 molecule of iodine. Same thing with moles. 2 moles of hydrogen iodide decompose, I make 1 mole of hydrogen gas, I make 1 mole of iodine gas. So what is my overall change? My starting value minus whatever the decomposition is of hydrogen iodide. And when this decomposes, I make half the number of hydrogen and iodine molecules because the original ratio is 2 to 1. So every 2 of these, I make one of these. For every one of these, I make 1/2 of these. For every 4 of these, I make 2 of these, if that helps explain it a little bit better. So now I have equilibrium concentrations, and I have my equilibrium constant expression already. So now I'm going to plug these into my equilibrium constant equation. Now you'll notice that we now have we had to do algebraic FOIL in order to factor out this particular square. But we end up getting this equation, this I forget the algebraic term, this component equaling the equilibrium constant. Now, we'll just do some manipulation here. We end up multiplying both sides by what's on the bottom in order to get it on the top. Now I move all of my numbers over by subtracting in order to actually take care of the 2x squareds on either side. I'm going to subtract this from x squared, or 1x. So I end up getting this over, I subtract this over, get a positive number, subtract this over, get a negative number. 0 equals something to x squared, something x, something with a number. That might look familiar. If it doesn't, it's where you put in the quadratic formula. So we're going to plug in these values, my b, negative b, my a, my c value. So I end up getting negative b plus or minus b squared minus 4ac over 2a. Someone was singing the song about that. I plug in my values. I end up getting 2 possible values, which I forgot to animate here at the bottom, and my apologies. I thought I had taken care of all of my animations. But I end up getting 2 possible values. Now, for the top one to be true, for x to be a negative number, that means that my original ice table, this would be a positive. My hydrogen iodide would increase in concentration from the original. That's not possible. It would also mean that my hydrogen would decrease from 0. Also not possible. Mathematically okay, in certain weird calculations in some other discipline, maybe that's possible. It's not possible in chemistry. You can't have negative atoms, negative molecules. Doesn't happen. There's no way of expressing that in this particular expression. So only one of these is valid, which is the positive number. So yes, if it's a positive number, then my hydrogen iodide concentration goes down. My hydrogen and my iodine concentrations go up. So 0.800 minus 2 times x, and x was 0.081, 6.838 molar at the end, and my hydrogen and iodine have to be equivalent, because for every 2 moles of hydrogen iodide to decompose, I have to make 1 mole of this and 1 mole of that. There's no other possible way. So these 2 concentrations have to be equivalent. Now, if we remember our original equilibrium expression was 0.016, which meant that our reactants were favored over products. And if we get to the end here, we can see that our reactant is more highly concentrated than our products. Okay, now, I think I'll just steamroll ahead through. No, I'll leave this as it is for now. And I will get to the packet problems on a following video. Thank you.